Well, hello, kinesiology students. It's Mr. Krenta here, and today we're talking about energy systems. Where do we get our ATP from? That's really the question we're answering here. We know from looking at the sliding filament theory of muscle contraction that we need ATP to run that contraction system. ATP is what breaks the bond between actin and myosin, and then it's going to break down to provide the energy for that myosin head to cock back, reattach, and then continue to slide the actin in towards the midline. So that is this whole system is predicated on, do we have enough ATP to run it? As long as we have ATP there, we can run that system. And that is really what we're looking at here. How do we get the ATP into our muscles? Where do we get that from? And there are three different ways that our body produces ATP, and those are our energy systems. So let's start with ATP here real quick, just to recap. So ATP we know is called adenosine triphosphate, and it is an adenosine molecule, and it is attached to three phosphates, triphosphate, right? Three phosphates to it. Now, in the presence of water, in a process called hydrolysis, but in the presence of water, one ATP will break down and release one phosphate. So here's my water, and I've broken off one of my phosphates, and that releases energy. Okay, that's my energy release. What I'm left with is ADP, so adenosine diphosphate. So ADP is the result, and then I have this free phosphate that will be floating around. So the ADP can recombine with phosphate to make more ATP. And that's really what the energy systems try to do, is put phosphate back onto ADP to make ATP, triphosphate again. And then in the presence of water, bang, that reaction will occur and energy will be released for the muscles to contract. And that's what your energy systems provide. And that's why we call ATP the energy currency of your body. It is the way that energy is transferred around in your body. It's through ATP. It's the that we have money, and then there's value on the money. Well, we've got the value is energy, but the mode of transport is ATP. So the more ATP we have available, the more things that we can do, and your body provides it in different ways. Now, the reason why your body provides it in different ways, different systems, primarily is because you need energy in different ways at different times. Sometimes you need a lot of energy really quickly. When you're doing high intensity power activities, you need a lot of energy really quick to do a sprint or a power lift, but you don't need it for very long, or at least you can't have it for very long. So a lot of energy all at once. But sometimes you gotta make it last. You gotta be able to do something for a long period of time. And so your energy systems shift based on your energy needs. What do you need in the moment? Now, we're human, we're not Superman or Superwomen. So there's limitations, obviously, to our energy systems, but that's the difference. You can think of like shifting gears in a car. Based on what the car needs, we shift into a different gear, and that's a little bit what our energy systems do for us. Two big overarching topics or titles to our energy systems are anaerobic and aerobic. Anaerobic means no oxygen, and obviously aerobic means with oxygen present. So we have two systems that are anaerobic, and we have one system that's aerobic. Okay, so where do we get the ATP from? So let's go. First system is our ATP-PC system, or our immediate alactic system. I'll tend to use immediate alactic, but either way, all these names are interchangeable. So ATP-PC or immediate alactic. If I told you start sprinting as fast as you can, what you would be doing is using your ATP-PC or immediate alactic system. That's a system that's going to get you a lot of energy fast. Now, it's not going to last very long, as we'll see in a second, but it gets you a lot of energy fast. What is the fuel for this system? Well, just like it sounds, ATP and PC. So ATP, you have a short amount of store of ATP that's just ready to go in your muscles already. And then you have this product called phosphocreatine. And phosphocreatine exists primarily in our fast twitch muscle fibers. And phosphocreatine is just like it sounds. It's got a creatine molecule and it's attached to one phosphate. So I have ATP and creatine phosphate in those fast twitch molecules. What happens with this system, the reaction that occurs, is I've got ADP left over, right? I'm trying to recombine a phosphate to ADP to make ATP. And so here's my phosphocreatine right here. And through the reaction, it's just one quick reaction, the P in the PC breaks, and I donate this phosphate to the ADP to make ATP. So I get an ATP molecule out of it, and then I've got some creatine left over. So that's what happens with that system. Now, what happens with that reaction is for every molecule of phosphocreatine that I have, I get one ATP out of it. So it's a 1-to-1 ratio. So if I gave you 4 quarters and you gave me $1 back, that would be just a fair trade, right? 1-for-1 exchange. But the thing is, we'll find out soon, is that this equation is very short. So I can get it very quickly. One quick reaction, and I can get an ATP out of it. Now, I only use this for high intensity activity. So if I want a lot of energy really quickly, I'm going to use my immediate alactic system for that, because the reaction is very fast. It's very short, so I can get energy very, very quickly. I can use the system for about 10 to 15 seconds. 15 would be max. Usually around 10 seconds is the amount of time I can use this system for. What you have in this system is you have about 1 to 2 seconds worth of ATP just ready to go. So I've got 1 to 2 seconds worth of ATP, and in that first 2 seconds of really intense activity, I'm just using the ATP. Once my ATP runs out, 2 seconds, then I'm starting to use the phosphocreatine that's in my muscles. And I've got about 9 to about 13 seconds worth of phosphocreatine. That's just all the amount that my muscles can store. And if I want to train, I can put more phosphocreatine in my muscles, not a lot more, but I can put a little bit more. But for all of us, we have definitely a limit of around 9 to 13 seconds worth of phosphocreatine. So super intense, I'm sprinting that first 2 seconds, ATP, and now I'm burning phosphocreatine, and that can last for about 9 to 13 seconds, okay? And then that's it. And then I'm out, I'm done. I can't use that system anymore until I rest, essentially. When I'm using my aerobic system, then I can, the creatine will combine with the free phosphates and make phosphocreatine again. And then it's ready to go. I've replenished my stores of creatine phosphate, ready to be broken down to make more ATP. So my limit with my immediate alactic system is how much available phosphocreatine do I have. So the more phosphocreatine I have, the more I can use that system, but I don't have that much, so it limits me to only about 10 seconds, maybe 15 seconds worth of high intensity activity with that system. Creatine is the waste product. So I just got creatine sitting there, and without the phosphate attached to it, then I don't have the ability to really produce any more energy. So creatine is just there, and then when free phosphates are available, it recombines into phosphocreatine. So who uses this system? Well, sprinters, we talked about, like 100-meter dash, 40-meter dash, 100-meter dash, anything 15 seconds or less, that's what you're looking at for your ATP PC system. Somebody like a weightlifter, an Olympic weightlifter, is doing one big lift. You know, it takes 2, 3, 4 seconds to do. That's your immediate lactic system. It's super fast, super quick. And, if I'm doing a gymnastics vault and I just got one big move to do, boom, and it's done. Anything that lasts about 10 seconds worth of high intensity activity, that's where you are using your immediate lactic system. When you train your immediate lactic system, what you do is you can slightly increase your amount of ATP stored. So rather than have 1 second, I might have 2 seconds worth of ATP in my muscles. And your phosphocreatine stores you can increase if you train this system. I can only increase it by about 20 to 40%. It's not like I can, double or triple my phosphocreatine. I can only add, instead of 9 seconds, I can have 12 or 13 seconds worth of phosphocreatine if I really, really train this system. So that's the first system. So if I told you to sprint as fast as you can, immediate lactic system. Fast, short reaction, 1 molecule of ATP for every molecule of phosphocreatine. Now, I've asked you to sprint for 10 seconds, and now I'm asking you to sprint for longer, as hard as you can. Go past 10, 15 seconds. Then we switch over to the next energy system, which is glycolysis, or the short-term lactic acid system. The fuel for this system is glucose. Okay, glucose. It's the simplest form of carbohydrate. When we consume carbohydrates, they break down eventually into glucose. And this is the only fuel source for this system. And this is why, if you've, an athlete that you're probably told, have a high carbohydrate diet and just before an event, it's because you want glucose available when you need it to be able to use this system. So glucose is a 6-carbon chain. That's what I'm representing here. And what happens with the reaction in about 11-step reaction. So remember, we had 1 step here, and we've got 11 steps here. It's a longer reaction. This reaction called glycolysis. It takes about 11 steps. And what you're doing is you're breaking down this 6-carbon chain in half, and then eventually breaking it down into something called pyruvic acid. And then you are exercising at such a high intensity, you don't have enough oxygen to do anything else with pyruvic acid except to, it'll turn into lactic acid, which we'll talk about in a second. But you need to use ATP in order to break this bond, in order to break down glucose. It's a tough kind of molecule to break down. So these 11 steps use 2 ATP to break down the glucose. But when you convert it, you get 4 ATP out of it. Okay, so you'll use 2 and then you gain 4. So what is your net total ATP out of 1 molecule of glucose? Well, 4 minus 2 equals, 2. Good job. So for every molecule of glucose, you get 2 ATP out of this system. Okay, so that's a bit better than my immediate lactic system. If you gave me $1 and I gave you $2 back, you'd be like, yeah, I'll take that. I'll take that investment of, doubling my money. That's a better outcome for ATP. So I get a little bit more ATP for every molecule of glucose. Now, remember, it takes 11 steps. So I don't get it as quickly. That's why it takes, that 10, 15 seconds to be able to break down glucose enough that I'm getting the 1-for-2 ratio, because it's a longer reaction. You're using this when there's high intensity activity as well. So if I told you to sprint and don't stop for about 2-3 minutes as hard as you can, you'd be using this system a lot. It's for high intensity activity. If I lower the intensity, I get enough oxygen to run my aerobic system. But I'm going at such a high intensity, I'm not getting enough oxygen, so I am just using this system. So the timing is about 15 seconds, so like once I use up all of my phosphocreatine, till about 3 minutes or so. This is a little fuzzy. It depends on your training. Depends on your muscle makeup, your muscle fiber makeup, type 1 or type 2. But around 3 minutes is what we're going to say for our lactic acid system, our short-term lactic acid system. Now, why 3 minutes? Why can't I use this system, this 2-for-1 ratio, longer than 3 minutes? Well, the answer is this: lactic acid. Okay, the waste product for this system, once I get it down to pyruvic acid, if there's no oxygen present, then that pyruvic acid gets turned into lactic acid. Lactic acid is not your friend when you're exercising. Okay, maybe you've heard of lactic acid before, but if I produce a lot of lactic acid, all of a sudden I can't react the same way in glycolysis. It slows the reaction down. Okay, the acidic nature of lactic acid really slows down this 11-step process to break down glucose. So all of a sudden, I can't produce the same amount of ATP anymore because the reaction is really slowing down. It's also incredibly painful for our muscles to have lactic acid accumulation. So you've probably been in this situation before, being great athletes where you've been working really hard, and all of a sudden it's like you get that really sore feeling in your muscles, right? That intense soreness where you feel like you can't go any further, you can't go any, like that's the lactic acid production going on. So it's very painful. Your muscles can't, your body is going to react and say, stop it, stop it, stop it. And you're not going to be able to keep using that system anymore because it's so painful. You also have hydrogen ions, and I don't have time to get into the nitty gritty of this, but hydrogen ions are a byproduct of this as well. And they inhibit calcium from binding to the during the system where we're doing the sliding filament theory of muscle contraction. If you remember, the calcium is released from the sarcoplasmic reticulum, and hydrogen ions get in the way. So now all of a sudden you can't have that same contraction with the sliding filament theory anymore. So we can take lactic acid and we can convert it back into glucose if we want to. So it can be turned back into glucose. But it takes about 6 ATP to turn our lactic acid back into glucose. It's a process called gluconeogenesis. So if I'm producing 2 ATP, but it takes me 6 ATP in order to convert it back, I'm losing 4 ATP when I'm building up the lactic acid. And so I can't indefinitely keep accumulating all this lactic acid and still run the system, because I will lose 4 ATP by converting lactic acid back into glucose. So it's not sustainable. I can't keep, if I put more garbage in my house that I'm taking out, eventually my house is going to be full of garbage, right? So that's the same way with lactic acid. And that's why the limit is about 3 minutes. So who is using this system? Well, anybody who's doing high intensity activity for longer than 15 seconds. Okay. So you think our 200 to 800 meter sprinters are really high lactic acid athletes. If you think of hockey, a sport like hockey, how long are the shifts in hockey? Well, they're probably about 40 seconds is a long shift, maybe 30 seconds, and that's just pure lactic acid. 50 to 200 meter swimmers, where you're going at a high intensity for longer than 15 seconds, but around that 3 minute mark. Those would be the kind of athletes who use your short-term lactic acid system. Now, athletes in team sports use this as well. Just like they use the immediate lactic system. It just depends on the situation. So let's say I'm a soccer player. Well, if I need to sprint for the ball really quick and I have phosphocreatine available, then I'm going to use that system, my immediate lactic system, to sprint for the ball. Now, if it's a play that I'm running hard for longer than 15 seconds, it's a 30-second, I'm running hard, it's in my zone, and I'm constantly moving at a high intensity, well, I'm going to be using the short-term lactic acid system. Just depends on the situation that we're in. Now, if you train this system, what happens? If you train your short-term lactic acid system, you've got faster gluconeogenesis. So that means I can turn lactic acid back into glucose faster, which is great. So I can, instead of 2 minutes, I can last for 3 minutes, maybe even 4 minutes if I'm really training hard. So I have faster gluconeogenesis. I have a higher pain tolerance if I train. So if you're training your lactic acid system, you just your body gets used to the pain, and you don't throw up when you work out that hard anymore because your body changes and gets used to that type of lactic acid production. So there's a pain tolerance that you develop there. And then the aerobic switch. So if I can go at a fairly high intensity and use my aerobic system, that's much better because I can use that system for much longer. So if you train your short-term lactic acid system, you actually develop the ability to go at a slightly higher intensity and utilize your aerobic system a bit more at the same intensity level. Okay, so I'm at the same intensity level, but I'm not producing as much lactic acid because I'm using my aerobic system at that intensity. Whereas person B who didn't train, they're just using their lactic acid system and they're just accumulating lactic acid. Whereas I'm at the same intensity, but I'm using my aerobic system. I'm not producing the same amount of lactic acid, if that makes sense. Okay. So short-term lactic acid system, glucose is the fuel. 1 molecule of glucose gets me 2 ATP, and my limiting factor is lactic acid. The last system, the system that our body always prefers, that I'm using right now, not doing anything, that you're probably using right now, sitting down watching this. And if you're doing a low intensity jog on a treadmill, you're going to use your long-term oxygen system, okay, or cellular respiration. This is our aerobic system. And our body prefers this because I can use lots of fuel sources and I get a ton of ATP from those fuel sources using this system. Okay, so first let's look at the fuel. The fuel for this system is glucose. Again, I can use glucose in order to use the long-term oxygen system. Fats, I can use fatty acids in order to use this system as well. And I can use protein. Now, your body really doesn't want to use protein in order to create energy. It really wants to use protein to build, your actin and myosin filaments are made of protein, and a lot of your other bodies, they're like building blocks of your body, right? Protein. So using protein is only in extreme situations, like if you're in a starvation mode, will you start to burn protein? You start breaking down your muscle in order to provide energy for yourself, which you don't want to do. It's like tearing down your house to make a fire in order to keep yourself warm. You wouldn't want to do that. So we really kind of focus on glucose, carbohydrates, glucose, and fats for our long-term oxygen. So I've got options. Now, the reaction for cellular respiration is very long, and there are many, many reactions in order to produce the ATP in this system. And if you're taking biology, you probably had a look at this, but you understand more. Like there's a long process, which is just outside the scope of this course. But basically, there's many, many reactions. Once I have pyruvic acid, remember glucose in my short-term lactic acid system was converted to pyruvic acid. With no oxygen, it got converted into what? Lactic acid. Now, if I have pyruvic acid, but I have lots of oxygen, so I'm not going at such a high intensity that I don't have any oxygen available, I can take deep breaths, and I have a lot of oxygen available to me. Then it gets converted into something else. It's called acetyl-CoA. Okay, acetyl-CoA, it can be utilized into the Krebs cycle, and I get ATP out of the Krebs cycle, and it can go through the electron transport chain. ETC is the electron transport chain, and through a series of reactions, I can get a lot of ATP out of the electron transport chain with the products that I get from the Krebs cycle. Again, outside of the scope of this course right now, but those are the main reactions that are causing you to get a lot of ATP out of this system. So with a lot of oxygen, I can take pyruvic acid and I can turn it into acetyl-CoA and turn it into all kinds of ATP. How much ATP? For every molecule of glucose or fat or protein, I can get about 36 ATP. Okay? It varies based on your body situation, but 1 to 36. Now, if you gave me $1 and I gave you back $36, you'd like that a lot. That's quite the investment, right? So your body thinks the same way. For every molecule of glucose, if I can get 36 ATP out of it, that is fantastic. So this is why it's your body's preferred mode of getting ATP. Okay, so 1 to 36 ratio. Now you can only get this if you have enough oxygen. You only have enough oxygen if the activity is a low enough intensity. If I'm going at a super high intensity, I need a lot of energy fast, I don't have time to suck in all the oxygen that I need in order to run the system, then I'm going to use the other systems. But if I have a lower intensity where I can constantly get all the oxygen that's required, then it's going to utilize this system. So if I told you to sprint as fast as you can, don't stop running. First, you use your ATP system, your ATP PC system. Then, if you didn't stop after 15 seconds, hard as you can, you switch over to your glycolysis, your short-term lactic acid. And then if you went past 3 minutes, you would notice a sizable drop in your intensity. You get a lot slower after that time frame. But probably what you'd find is you'd level off a lot. You could sustain that level of intensity. So high intensity with immediate lactic, and then after 15 seconds, you notice a drop in intensity slightly, and you'd be in your short-term lactic acid system. And then you notice a sizable drop, and then you'd be able to sustain this for a long time because you're getting all kinds of ATP. But it has to be lower intensity. You can't have that high intensity because you're not getting enough oxygen in the time frame. Okay? And this is where, because we're getting so much ATP, once I get into that system, I can start replenishing my other systems because I have so much ATP available to run gluconeogenesis, to take creatine and add phosphate to it, right? So I can replenish those stores once I get into this, generating all this ATP. But it has to be low intensity. So timing of this, once I hit that 3-minute mark, then I'm kind of switching over. Again, it's a little bit fuzzy depending on who you are, how much training you have. But generally, we say after 3 minutes of activity, then you're starting to get into your long-term oxygen aerobic system. All the way up to 3 hours. Like if you think of running a marathon, you're going to run that period of time. Obviously, our bodies are amazing and can push themselves for longer. And really, we are always using, at rest, we're using our long-term oxygen system. So when do we stop using our long-term oxygen system? We kind of really don't. So after I finish the 3-hour marathon, I stop. What system am I using? I'm still using my long-term oxygen system. I just have dropped the intensity level down to next to 0. And so I can recover. But I'm using it for a long period of time, right? So once I get to that 3-minute and almost indefinitely, I'm using that long-term oxygen system. So what's the limit? Well, it's the activity intensity. So I can't use a system and go at a high intensity, right? I can't sprint a marathon, right? Unless you're Eliud Kipchoge, which you should look him up, and that guy's pretty amazing. But anyways, you can't have that high intensity and sustain it past that time frame. That's when you're using these systems. So really the limit is the intensity of your activity and the amount of fuel, the availability of fuel, right? You can go and then some runners call it hitting a wall or bonking, where you run out of glucose or you run out of available energy, and all of a sudden you can't really go anymore. So you got to have that energy available to you. So just making sure you're fueled while you're doing your long-term oxygen system training. What's the waste product? Carbon dioxide and water. And that's really what we breathe out, right? So we're breathing out carbon dioxide, and there's water in our breath. So when we expire, that's our waste product. So it's a pretty efficient system. It's actually an incredibly efficient system. And our those waste products just exit us in the air, and they're not bad for us. They're actually good for plants, obviously, and for the rest of our world. But those are your waste products there: carbon dioxide and water. So who's doing this? Who's using this system a lot? Well, obviously our marathon runners are using this system. Our 1500 meter plus swimmers, our endurance swimmers, our triathletes are using this system pretty much exclusively. So those long distance type of activities are where you're using your long-term oxygen system. If you train this energy system, what happens? Well, you get a larger and stronger heart. You get more red blood cells, which allows you to utilize oxygen better. And you get more efficient Krebs cycle, so I can run that reaction a bit quicker and get more ATP out of it. And more fat usage. It's better to use fat than carbohydrates because it's got a lot more energy packed into fat. So utilizing fats is a good thing for our body. And you can tell the body type of marathon runners, very low body fat percentage, because they're constantly burning that fat. So there you go. There's your energy systems. You have a wide range, and you've got different energy systems for different reasons, different times when you need it. So just look through the systems and make sure you have an understanding of the fuel, the ratio, what the limits are, and who uses it, and what happens when you train that system. Thanks, guys.